Okay, so in this video we're going to talk about the mean value theorem for integration. So the mean value theorem for integration. Before we talked about the mean value theorem for differentiation. So let f be continuous on the interval a to b, continuity on ab. Then there exists a c value in ab such that the definite integral from a to b of f of x dx is equal to f evaluated at that c value that's in between a and b times b minus a. So what does this look like in a picture? Because I think a picture will be able to explain this a little bit better. So let's draw a graph of a function f. And we're going to start and we're going to take the integral from a to b. So we're going to go from a to b here. And so now what I'm going to do is I'm going to figure out how this is defined here, what this shape actually is. And so this is distance from A to B. So if this was like 2 and this was like 7, how would I find the distance? I would do 7 minus 2, right? So that's B minus A. So that's the distance right there. So the bottom side of that red rectangle. All right, now what about C? So C is some value. I plug a C in. C is between A and B here. When I plug C into my function, I get f of C here. So the height of this rectangle is represented by f of C. So the height is f of C. The base is b minus a. So what does b minus a times f of c represent? Well, I'll tell you what it represents. Base times height for a rectangle represents the area of a rectangle, okay? So this is equal, what we're saying is the definite integral from a to b, this weird looking shape right here, so the area under the curve from a to b is literally equal to the area of this rectangular shape right here. Okay. Which is kind of an interesting fact. So what is that saying? I know that it doesn't look like it graphically, but what this is technically saying is that this blue area right here that's over that line is equal to this red area right here that's under that line. So maybe this isn't, the bar isn't exactly where it should be. Maybe it should be a little bit higher so that we see like we had like the exact same amount of area up and above. But that's just the fault of me by not drawing a perfect picture. Okay? So kind of a cool thing here. So what this does is it kind of gives us like this average value of the function f on such an interval here, which is kind of a weird concept because when I think about averaging numbers, I usually have like a finite list, like 5 plus 7 plus 22 plus 15. And then I take how many there are and I divide by 4. But whenever I average over this interval, I'm actually considering an infinite number of points on that interval there. So it's very different. So interesting idea going on there. Okay, so this theorem only tells us that there's a C that exists, okay? It doesn't tell us what the value of C is or how to find it. It just tells us that there's some value between A and B where if I plug in f of C, this horizontal line here is going to represent the height and the base here multiplied together gets you that average, that area equal to the definite integral, okay, which produces that average value. So what I want to do now, instead of just knowing, hey, look, it exists by the mean value theorem, I want to find the value C that's guaranteed by the mean value theorem. And so I'm given a particular function, okay? So what I'm going to do is I'm going to take this first and I'm going to use my theorem here. So what I want is the integral of f of x dx, so my f of x is the cube root of x, equal to f of c times b minus a. Now what is going on here? A is the lower limit, okay, and b is the upper limit here. So that's where I get my numbers from. So for this particular problem, my b is 8, and so I do 8 minus, and then my a is 0, 8 minus 0 going on right there. So let's plug it in. So what does this tell me? All right. So what I want is the definite integral from 0 to 8 of the cube root of x dx equal to f of c times 8 minus 0. So what I want to do is I want to solve this equation for the variable c. Okay, so I want to solve that for c. So the first thing I need to know is what in the world does this equal to? Remember, the definite integral produces a number, correct? So this is just going to be some number. So we need to figure out what that number is. And so I'll have some number equals f of c times 8. And so if I divide both sides by that number, then I know what f of c is, and I can solve for c. So let's compute the definite integral real fast. To do that, I'm going to convert this to rational exponent form. Remember the rider and the horsey trick. The rider goes in the house, the rider goes on top, the horsey goes outside, and the horsey goes underneath whenever you're riding, right? So that's going to be x to the 1/3. Whenever I add 1 to 1/3, 1 plus a third gets me, well, that becomes 3/3. So that's 4/3 as an exponent. But when I divide by 4/3, when I divide a number, I do the reciprocal, right? So that becomes 3/4, multiplying by 3/4. And so I want to integrate this from 0 to 8. So I use the fundamental theorem of calculus part 2, f of 8 minus f of 0, f of b minus f of a, right? And so I'm going to plug in 8 into the antiderivative. And so when I plug in 8, everywhere I see an x, I'm going to get 3/4 cube root of something raised to the 4th power, right? And so I plug an 8 in there. The cube root of 8, something I multiply by itself 3 times, that's 2, okay? So what do I have? I have 3/4 times 2 raised to the 4th power. And to simplify this, I do 2 times 2 times 2 times 2, 2, 2, 2, 2, and then I'm dividing by 4 and multiplying by 3. That's what's going on with that 3/4. So 2 and 2 cancels there, so I have 4 times 3 is 12. Okay? You can use your calculator to get this answer for you. So what does that tell me? So that tells me that my definite integral here, this answer right here, is just 12. Okay? So 12 is equal to f of c. Now what is f of c? Well, f of x is defined to be this integrand right here, right? That's what we have right there, okay? So that is defined to be the cube root of x. So f of c is going to be the cube root of c. Everywhere I see a x, I plug in a c. Okay? Multiplied by 8. So now all it amounts to doing is figuring out what c is. I'm going to divide both sides by 8. So 12 divided by 8 is going to reduce to 3/2. To get rid of a cube root, I'm going to cube both sides. When I cube both sides, I get 3 cubed over 2 cubed. 3 times 3 times 3 happens to be 27. And then divide by 2 times 2 times 2, which is 8. So my c here is equal to 27/8. Kind of cool, all right? So if you looked at this like as a picture, okay, I'm going to do my best to draw this in here, okay? So my interval is from 0 to 8. Now cube root of 8 is 2, so I'm going to go at 1, 2. So this point here, and at x equal to 1, I actually have a 1 there. 1, 2, 3, 4. Oh man. 5, 6, 7, and then 8. Okay, so let me move this over here. All right, so I'm trying to get this as best as I can to 0. So the cube root kind of looks like this, and then it goes in the other direction like this. So I want to know the value that I can plug in here. So 27 over 8, what is that? 27 over 8 is 3.75. So that is 3.75. So that's like 1, 2, 3. So somewhere in here. So the value here, so this is the C value, but that's between your A and your B, right? And so you come up to this point right here, and then so you make your line across just like this. And so the area in this box right here, so this area in that little box right there, which it's easy to find the area of a rectangle, okay, is equivalent to the area under the curve, this blue shaded region here, okay? So geometry would tell us that the area difference that is found in here is equal to that area over here, okay? And so what we'll learn in the next video is about the average value of the function f. Like, see, at x equal to 0, f is equal to 0 over here, right? At f equal to 1, or x equal to 1, I have a f value of 1. At x equal to 8, I have a f value of 2. So if I took like all of these numbers, like all on this curve, the infinitely many numbers that I had, and I averaged all those numbers together, that's a lot of numbers. There's infinitely many numbers, many dots that I can put on that curve, right? If I average all of those values, then that average value is equal to f of c, which is f of, what did we say, 27 over 8, right? So that would be equal to the cube root of 27 over 8, which is 3 over 2, right? So the average value is 1.5, all right? So the f values range from 0 to 2, but 1.5 is that average value on the interval. Okay, so kind of an interesting idea here. All right, and when you're talking about trying to find like a continuous average like this, like an example would be like if you've got like temperature throughout the day. Okay, so like the temperature in the middle of the day, like at noon, is going to be pretty high, right? So that like at 12 noon, that's pretty hot. But at like 12 at midnight, it might be like the coolest time of the day. So if you're wanting to find the average temperature throughout the whole 24-hour period, then you may want to consider using the mean value theorem, mean meaning that average value, right, over some particular interval. And that's where calculus comes into play, because there's no way to add up an infinite number of values without using calculus. Now, what you could do without using calculus is just say, all right, I'm going to take the temperature at 12 noon. I'm going to take the temperature again at 1. I'm going to take the temperature again at 2, 3, 4, 5, 6, all the way through and get 24 temperatures and then average those temperatures. And you'd probably get pretty close to the true average, but calculus lets you take that one step further